Hello everyone. Today, we're going to learn how to design earthquake-resistant structures in the simplest way possible, along with special tips to help you reduce construction costs while keeping the structure strong, safe, and compliant with engineering standards. The units we'll use for the design are as follows. Let's start the project. Enter the project name. The first floor beam level is at plus 0.3 meters. The wind load used in calculations is 60 kilograms per square meter. Step 1. Draw the beam layout. Start by setting the beam span and choosing the beam direction. Double-click to enter selection mode. Select the beam whose spacing you want to copy. Swipe in the desired direction. The beam will be created from the reference point to the next grid line. Double-click again to exit selection mode. Move the reference point to a new position. Move the reference point 1 meter to the right. Swipe down to create the next beam. How to zoom in and out. Pinch to zoom in. Tap to lock the screen. Swipe right. Press undo. Pinch out to zoom out. Next, create the second floor by copying the beams from the first floor. The beam level is at plus 3.10 meters. Double-click to enter selection mode. Select the unwanted beams and press delete. Finish drawing the second floor beams. Step 2. Input loads and wall weights. For live load, we'll use 200 kilograms per square meter. For precast floors, we'll add the self-weight of the slab, using a value of 300 kilograms per square meter. For cast-in-place slabs, the system will automatically add slab weight after design. But for safety, we'll predefine it as 300 kilograms per square meter, same as precast slabs, to allow for topping and leveling. Now, input wall loads. Select the wall position. The wall is made of clay bricks, weighing 200 kilograms per square meter. The wall height is 2.8 meters minus the beam height of 0.4 meters, which equals 2.4 meters. Multiply the wall weight by its height to get 480 kilograms per meter. Input the weight with more detailed values. Use the slider to adjust dimensions. Continue with the second floor. For the cantilevered balcony area, since it's thin and lacks external beam support, we must design it as a cantilevered slab only. A recommended technique is to cast the in-situ slab with anchorage that extends farther inward than the cantilever span. This enhances the strength of the cantilevered slab. After that, pour a topping layer to level the slab. Once the design approach is defined, go back and add beams to support the cast-in-place slab. Create the cantilever slab. Ensure all reference points and dimensions are specified. Create the staircase and define its parameters. Live load for the stairs is 200 kg per square meter. For dead load, we'll only add the weight of finishing materials, 50 kg per square meter. Select the stair zone. Step 3. Set design parameters for beams and slabs. In this step, we'll design using the strength design method, applying safety factors according to structural engineering standards. One key technique to optimize cost is choosing South Dakota 40 grade rebar, which has a tensile strength of 4,000 kg per square centimeter, compared to 3,000 kg per square centimeter for SD30. This means South Dakota 40 can handle about 25% more tensile force than SD30. The advantage of South Dakota 40 is that it allows you to reduce the amount of steel needed. And importantly, its price is similar to South Dakota 30. But remember, the steel used in construction must match the grades specified in the design to ensure safety and performance. Auto RC is designed to analyze structural behavior under multiple load cases simultaneously. The system will select the critical values from each case for use in the final structural design. The analysis combines traditional beam analysis with full 3D analysis. In beam analysis, supports are defined as pinned to prevent structural failure even if the joints are compromised. We'll use an automatic section guide design system, allowing the program to generate beam sections that closely match our intended specifications. Name the beam group. Assign a name to the beam group, specify the section name, and enter the desired section dimensions. Keep in mind that these settings are just preliminary guidelines for the program. Ultimately, the program will automatically select the safest and most suitable section for the design. Step 4. Merging floor plans and creating the model. Since we're using the Pro mode, the floor plans were already merged during the drafting process. So in this step, we'll focus on creating the roof and beam models. Start by creating the tie beams. Use the elevation level of plus 5.80 meters as a reference. Select a reference point, then drag to highlight the entire area where tie beams are to be placed. Next, proceed to model the roof. In this case, the roof is a gable tile roof with a 0.80 meter overhang beyond the building edge. The roof load will be based on the data provided in the table. Adjust the roof structure. Hide parts of the model to make editing easier. Then move the king post to align properly with the tie beam. Remove any unnecessary existing beams. Add another king post as needed. If any component, such as steel members, appears in red, it means that the element has failed the design check. In that case, select the failed tie beam. Click Edit and switch to a larger cross-section. If the desired steel section isn't available in the list, click Add New Section. Choose the section shape. Name it and enter the desired section dimensions. Step 5. Setting up column and foundation design parameters. We recommend using the strength design method for this project. The reinforcement used in this project is SD40 steel, with a yield strength of 4,000 kilograms per square centimeter. The foundation system used is pile foundations. We'll use 21-meter long I-section piles, each capable of bearing up to 15,000 kilograms. Set the allowable pile eccentricity at 50 millimeters in the design. This means the structure is still considered safe to build if the pile offset remains within the specified limit. Select the 3D analysis method for structural analysis. Configure the load combinations according to design standards to cover all possible critical load cases. Example of how to input the safety factor. For this example, we'll design the structure to withstand seismic forces equivalent to a magnitude 5 earthquake. We'll use a seismic response coefficient of 0.05. In the settings, ensure the structure accounts for seismic forces in all directions to ensure comprehensive and safe design behavior. Choose pinned supports. Step 6. Analysis data and design adjustments. We'll start by reviewing the overall structural components of the entire building. Go through each automatically designed component to identify which ones require further modification. Most of the beam groups follow the intended design approach. However, for the columns, we'll standardize the rebar type across the entire building to maintain construction consistency and quality control. Open the group editing mode for columns and foundations. Double-click to enter single floor view. Swipe up to navigate to the next floor. Then enable the batch edit mode. Select all columns on the current floor. Input the new cross-section size and reinforcement type. Next, we'll edit the columns on the remaining floors. Double-click again. Select all columns. Then go back to the ground floor. Select the ground floor columns again to deselect them. Change all reinforcement to DB16. Foundation design considerations. We can reduce the foundation size according to engineering standards. If the system-generated rebar quantity is insufficient, users can manually add more reinforcement. The number of piles can also be adjusted as needed. If the design fails, a warning color will be shown on the model. Whenever the structural cross-section is modified, the system will automatically reanalyze it. This may change the required rebar quantity, as the new cross-section affects the overall structural behavior. For example, in this column, the system automatically added rebar to satisfy the design criteria. It's recommended to add symmetric reinforcement on the opposite side to prevent construction errors and ensure structural balance. Adjust stirrup spacing to meet design requirements. How to verify column design pass or fail status. There are two main indicators. 1. Column color. If the design fails, the column will appear red or orange instead of blue. 2. Design graph. The white point must fall within the green line in every case. In this example, all columns meet the design requirements. Review the structural analysis data for the column with the highest deformation. It turns out the case with the highest deformation is the earthquake scenario. Check the reinforcement throughout the building. Hide the structural model view. Double-click to switch to single floor view. Swipe up to scroll through the floors. Reinforcement discontinuity was found in the beams on the second floor. Switch to selection mode. Select the beam clearly to highlight it. Navigate to the floor plan of the second floor. Edit the selected beam. The system indicates that the deformation per unit length exceeds the allowable limit. Since the beam is very short, close the warning first and review how much it deforms. Switch to DB20 rebar to ensure reinforcement continuity. The deformation warning shows only 4 mm, which is minimal. We'll leave it as is. However, if the system flags issues other than deformation, we must follow the recommendations immediately, as they could directly affect structural safety. For grouped structural elements, rebar can be safely adjusted. Note that the system prevents you from reducing the rebar below the minimum requirement, avoiding unintentional unsafe designs. This feature is useful for grouping similar structures to simplify the overall design set. Reinforcement in slabs can be adjusted similarly, with the system ensuring it stays within design limits. How to check if a beam has sufficient capacity. Check the critical moment value. The critical moment at the mid-span comes from beam analysis results. The nominal moment capacity (Mn) must be greater than the ultimate moment (Mu) for the beam to pass design. The critical moment at the beam ends is obtained from the 3D analysis case. Double-click to view the details. You can review both moment capacity and critical moments for the entire group. The system ensures that all values fall within the passing criteria. However, any failed design elements can be easily identified. 1. The beam will not appear blue. Click into the Edit page to see the specific issue and the system will suggest a solution. 2. If the reinforcement exceeds the cross-section capacity, it indicates insufficient strength. Increase the beam size to resolve this. Review reinforcement details. With detailed rebar specifications, we can optimize stirrup and reinforcement usage for greater cost efficiency. Things that can be done while maintaining safety include: 1. Using more frequent stirrups. 2. Using extended rebar lengths beyond the standard shown. How to rotate a foundation. Go to Edit Design. Select the foundation and rotate it. Modify the stair structure. Change the design to use DB12SD40 reinforcement bars. Step 7. Exporting data. In this step, we'll access various structural groups to prepare for data export. Export the calculation report booklet. The entire building's calculations will be exported together in a single document. The report displays calculations categorized by structural group. Prepare to export the bar cut list and shop drawings. The new settings allow precise control over rebar length ratios. We'll present a clear side-by-side comparison of the results. Standard reinforcement detailing. This method calculates cutoff points using moment values, ensuring the shortest permissible bar length is used. This method controls bar length based on beam ratios and ensures safety by not allowing bars shorter than the standard full span reinforcement method. This method is recommended as it's both cost-effective and safe, in line with construction standards. Stirrup reinforcement options. Uniform spacing along the beam. Reduced spacing based on shear force. Export shop drawings. The termination points of reinforcement and stirrup spacing are clearly detailed for actual construction use. Export the cost estimation file. You can find setup instructions in the Structural Design for Beginners video. Export as a PDF file. Export as an Excel file. Export as a CAD file. You can adjust font size and positioning before exporting. Export as a CAD file. Export the structural model file. It can be exported with or without reinforcement details. The exported model and CAD files. Download it for free using the link down in the description.